hear me on Zoom? Yes.
I hear you. I hear you.
Okay. Great, thank you. Okay. Great, so thank you everyone for coming today. I'm very excited to present some of my work on building deep learning theory in the age of generative AI. So over the past few years, we've seen a remarkable progress in AI capabilities, and this has led to models being incorporated into various products like chatbots from different companies, but also more productivity-oriented tools like code editors, search engines, and note-taking tools. Behind the scenes, all of this progress has come at a rapidly increasing cost. So the cost of training models has more than doubled every year, and this is especially true for language models, which are driving most of the products that I showed on the previous slide. Despite the increased investment into these models, as well as the excitement around them, we still have a very limited understanding. So by that, I mean, we have a limited understanding of how we should train these models in terms of what type of data set we should use, what type of model architecture, and what optimizer we should use. And also, as a result, we have little insight into how the resulting model will qualitatively behave. So for example, we might be interested in how factual the model is, how well it can reason to output new answers, and also how safe it is with respect to toxic content. So this means that if you had 10 different machine learning experts, they would actually give you 10 different ways to improve or to create the next generation of frontier models. And it's likely true that they would have little insight into how their scheme would qualitatively change the behavior of the model compared to another one. Okay, so in light of that, I'm proposing that we should actually be deriving a prescriptive theory. So what I mean by that is modern deep learning looks something like this, where we have a machine with a lot of bells and whistles, and you have a lot of people touching different parts of the pipeline. Indeed, companies can have hundreds or even thousands of people working to create a single model. Traditionally, to create deep learning theory, we isolate some component of this pipeline, we idealize it a little bit, and then we study it and understand it theoretically. And this has been great for gaining insights into what's going on in particular phases of the model creation. However, for this theory to be prescriptive, we need to complete the feedback loop and to be able to use the insights from the theory to design new algorithms. Traditionally, this has been a bit difficult for theory to do, and is becoming even more difficult as these models are trained in increasingly convoluted ways on more and more data, and the ways that we're training them are changing so quickly. So my approach to creating this prescriptive theory is what I call full stack. So on one end, we have theoretical or conceptual questions, like what do current language model training methods do, and how do these language models behave? On the other hand, we have a very simple practical question, which is just how do we get better language models for less money? So starting from the theoretical end, I build a theoretical description, and this requires substantially new tools to consider these modern settings that we're using to train these models. And then I actually verify that the theory is faithful. So all of my papers have a number of experiments in frontier settings to see that these theoretical descriptions are actually meaningful in the context of the models we're creating today. And finally, I apply the theory to design new methods. Most of my research has led in particular to efficient and effective training methodologies for creating these models. One thing I'll show in this talk today, which I can do with the benefit of time, is that the theory-motivated algorithms designed this way will work on settings that came out after the theory. So for most of the phases in my talk, I'll be showing some experiments that I ran just for the purposes of this talk, without doing any additional grid searches or modifications, to try my algorithms on new settings that came out after the theory was developed. So here's a more concrete overview of my work. Because it follows this three-stage process, a better understanding of these models actually does lead to an improved performance. So on the theory side, I built a foundational understanding of language models, in particular with respect to how they're pre-trained and fine-tuned, and I've also advanced our understanding of the stochastic optimization of neural networks. And this leads to impactful applications to efficiently optimize language models, understand the role of data, and also to identify, characterize, and mitigate failure modes that can occur in these language models. Because of the mathematical rigor of these ideas, as well as the broad applicability of the algorithms, Many of the algorithms are being used today in companies to develop their frontier models and reduce the cost of doing so. Today's talk will focus on 3 stages where I'll develop a prescriptive theory for pre-training, fine-tuning, and also training language models to obey human preferences. So let's take a look at pre-training, where our goal is to train new models from scratch efficiently. We've seen a massive investment in compute over the past few years, not only from the private sector, but also from the public sector, including my own school, Princeton. So one natural question to an outsider might be, what do we actually use all of this compute for? What we do is we scale or parallelize our training. And in particular, the most reliable way for us to accelerate the training of these models by an arbitrary factor is simply to increase the number of GPUs. So if you have the money, you can just buy more GPUs and finish training faster. So let's take a look at exactly how that works out. Suppose each GPU can process n examples. And by process, I mean that we need to run a forward pass through the model, as well as compute an estimate of the gradient. These days in machine learning, we use a mini batch to compute the estimate of what the dataset gradient is. So if we had k GPUs, then we could process n times k examples, and this would allow us to finish training k times faster. So like I said, this quantity of how many examples we can process at a time is known as a mini batch. And when we scale the number of GPUs, we also scale the mini batch size. The problem is that we have other sort of settings that we care about. So here I'm using the learning rate as an example, which is the step size that you take when you optimize the model. So we might have found the best learning rate at this small scale, but when we scale up, we're not sure what the best learning rate is. And in particular, we're using a lot more data to construct our estimate of the gradient. And so we might be more confident about the gradient, and maybe we should get more out of the optimization by taking a larger step. So maybe we should increase the learning rate. To this end, an empirical paper in 2017 suggested this idea of a linear scaling rule, where you scale the learning rate proportionally to the batch size. This worked well in practice, but conceptually, we might have a few other questions. Like, is that actually the best learning rate that we could use? And in particular, it's hard for us to run grid searches at scale using these k GPUs. And what happens when k goes to infinity? Can we truly buy more and more GPUs and become faster and faster with sort of no end in sight? Or is there actually a limit to the scaling that we can do? And I'm going to call this quantity the critical batch size, beyond which, if we increase the batch size, we're not going to finish training k times faster. It's actually going to be slower. And finally, this particular idea of a linear scaling rule was developed for SGD, which is an older optimizer. These days, language models, which benefit the most from this type of parallel training, are trained with Atom, which is an adaptive optimizer. So we might ask if this is the correct scaling rule for that. Was there a question?
Yeah, I just wanted to ask about the scaling law. So k times faster is scaling as a number of GPUs, but if you change the learning rate, doesn't that also accelerate? So you're kind of super k, aren't you?
Yes, so you should be able to, so I guess in the sort of naive case, if you don't change anything or get more out of increasing the number of GPUs, you should just go k times faster. There may be options, which is kind of also what I'm getting at, for setting the learning rate so you could go even faster. But actually, we'll show that that's not possible in general. Maybe in specific cases it is. Okay. So let me describe in terms of these 3 steps how we build a prescriptive theory for pre-training. So first, we build the theory using stochastic differential equations, or SDEs. And these are actually going to be an elegant model that are useful beyond just this parallel training question that I used to motivate here. We're going to verify the theory, which actually requires more theory to design an efficient and provably sound test to see if the SDE approximates training in any given setting. And we're going to run that test and see if it's true. And finally, we're going to use the theory. So we're going to develop a number of scaling rules that will allow us to scale to distributed training without requiring additional grid searches. And also, because we came up with these scaling rules theoretically, we can analyze when they're going to fail. So we can use a single baseline run, even at a small scale, to estimate the critical batch size, meaning we can say that If you gave us a run at a small scale, we'll tell you how far you can scale up and how many GPUs are actually worthwhile to buy. Okay, so let's see how this theoretical description of training works out. Suppose your neural network is like a baby trying to reach for the optimum, a rattle. So a very coordinated baby would take this sort of straight path directly to the toy. But we know that babies are sort of uncoordinated and wobbly. So they might take one of these black paths. If we were to plot the baby's position as a function of time, we would see that there's kind of this, it may be hard to see on the screen, but there's a shadow here, a green shadow that indicates some uncertainty in the position of the baby as time goes on. So this type of trajectory actually mimics what happens when we're training with gradient noise. Recall that we were using a mini batch of examples to estimate the gradient and optimize using that. So that induces some noise in the trajectory. So now one persistent phenomenon in deep learning, which we're not going to actually interrogate here, we're just going to take as a fact, is that the model with the best performance most often comes from this wobbly path. So if we take this sort of straight red path to the optimum, we're not going to do as well as this one where we kind of wobbled and went off path. So our goal is to model that stochastic path, since we want to capture the model with the good performance. To that end, there's this idea of using a stochastic differential equation to model SGD. So this operates in continuous time. So we look at how the parameters change in continuous time. And this is equal to a drift term where we follow the gradient, which is this red path, plus a diffusion term. So for the diffusion, we're going to use Brownian motion to model how the parameters may wobble on their way to the optimum. Now, this equation may look complicated, but the quantity that we actually care about is going to be 1 over b times sigma, because this is where the batch size shows up. And remember, we're changing the batch size, so this is the thing we care about. This sigma quantity is the covariance of the gradient noise. It's very hard to measure, but for our purposes, we're just going to treat it like a black box for that reason. So I also want to note that babies can kind of stumble and overcorrect in different ways. And this corresponds to how we have many different optimizers for machine learning. And each optimizer actually can possibly yield a different SDE. So a lot of my work has developed SDEs for different optimizers. Today, I'm going to focus on SGD because it's the most simple. Okay, so now that we kind of have a non-technical sketch, let's take a closer look at what these really look like. So the SDE is very general. It doesn't matter what architecture, data set, or objective that you're training with, you get one SDE for one optimizer. And it also doesn't require that you reach the optimum. So the model need not be anywhere near the optimum or the rattle in order for us to understand what's going on. It's also easy to make new SDEs for different optimizers. That's a technical contribution of our work and something that a lot of people have done as follow-ups. And as I mentioned, because of all these kind of general properties, the SDE is going to be useful beyond the parallelization question, though today I'm just going to focus on that. Okay, so technically, we face some additional challenges when we use this type of model. First, we need to define a notion of approximation that makes sense for stochastic paths. So here, recall that the baby's path had sort of a huge variance as to where the baby could be at any given time. So that makes it hard for us to say if two given paths are actually close to each other. And when we look at neural networks, things get even more complicated because networks with wildly different parameters could have highly similar performances. So for that reason, we also formulate a guarantee that's going to hold under many different test functions. You can think of this as something like measuring the test accuracy of the model. So prior work in this type of framework has said that the SDE for SGD is good when the learning rate becomes infinitesimally small or goes to 0. However, as that happens, the gradient noise is going to disappear. And so we're going to recover again that sort of straight shot red path, which we wanted to avoid because that doesn't yield a strong model. So the natural question is, we built this nice, elegant theoretical model, but is it actually a good approximation of real training settings? And in particular, to traditionally simulate the SDE would be way too expensive in the context of neural networks, and especially in the context of language models. So we need to develop a new simulation. So just to be clear, here's what we're doing. So we have this red path, which is what would happen if you sort of train a neural network ordinarily. You don't care about SDEs, you're just training it as you would. This blue path is sort of what our SDE is prescribing, though of course we're not able to usually plot it that way. What we do is we construct an efficient and provably sound simulation that's going to interpolate between this red path, the true training trajectory, and the blue one, our theoretical model of the trajectory. So this allows us to check if any given setting, meaning a new model architecture, data set, and objective, can be approximated by the SDE for this optimizer. So in order to do this more practically, you would get a plot like this. So there's a hyperparameter L that our simulation contains. When L equals 1, it reproduces this red sort of ordinary training trajectory. As you increase L, you become closer and closer to the SDE. You can see in this plot that by the end, this is the test accuracy plotted, you can see by the end that actually all of the trajectories converge to the same performance. So this indicates that the SDE is a good approximation for this setting. So this is an efficient simulation to run and can be run on many different settings. Here, I ran it for a vision model, but you can do so for a language model, and it's sort of a drop-in modification for any machine learning setting. Okay, so we built the theory, and now we sort of constructed at least a way to verify it, and we did verify it in our papers. So let's return to our original question, which kind of just boils down to asking, how should we change the learning rate when we change the batch size? So this was the SDE that we had, and we only care now about this blue term, which has both the learning rate and the batch size. So we can actually immediately recover the linear scaling rule from this, because when you scale the batch size, you need to scale the learning rate proportionally to preserve the SDE, to preserve the optimization dynamics. It turns out that if you follow the same steps for Atom, which is a popular optimizer for language models, then you'll see that you actually need to scale the learning rate by a factor of square root of what you scale the batch size by. So in practice, when we actually apply this square root scaling rule, you can see that we ran some language modeling settings here. We have other settings in our papers, but we're able to scale the batch size to an extremely large size without sacrificing the performance of the model. And here, when we scale up the batch size, we don't need to run multiple experiments. We just immediately use this scaling rule that's motivated from the theory. Okay, so now we return to another one of the questions we had, which is just how much can we parallelize? Can I increase the batch size to infinity? And if I keep buying GPUs, will I keep training faster and faster? So now that we've seen how the scaling rules sort of nicely fall out of the SDEs, we can actually say that when the SDE approximation is not good, the scaling rule itself may also not work. This allows us to measure the limits of parallelization from a single baseline run. Here's how that works. So on the y-axis here, we have some easily measured quantity. I won't get into the details of it, but it doesn't actually require a lot of compute. And so what you do is you train a model and you measure that quantity. So here, for example, maybe your baseline model is this green point, which has a relatively small batch size. So you can train this model on like 1 GPU, for example. Then you extrapolate the quantity across batch sizes, which is what yields this green line. And now when that quantity passes this black dashed threshold, that actually indicates where the critical batch size occurs. So that's this vertical dashed red line. And in particular, formally, what we're able to say is that at that critical batch size, the SDE is no longer a good approximation of the training, and thus the scaling rule may also fail. So if we compare our theoretical prediction against what happens when we train models with a bunch of different batch sizes, we see that it's often a sharp characterization of when the scaling rule does work. So you can actually use this theory-motivated prediction to predict when you will no longer be able to scale up and distribute your training. Okay, so as I mentioned, one thing I'm doing in this talk is presenting new rules that I sort of zero-shot ran on settings that came out after the theory. Here I'm using a Mamba model, which came out 1.5 years after we published the theory. And it still uses the Atom optimizer, so we can still use our Atom SDE and the square root scaling rule. But it's actually very different from other language models, the ones that I showed in the previous slides. And without getting into too many details, I'll say that we expect that the gradients for this model look very different from anything that we saw before. It's also going to be trained on a data set that's sort of new and is just a very highly filtered and high quality version of the internet. So we get a plot like this. So here our blue line is the baseline. And you can see that we reach a loss of 3 by the end of this rather short training budget. Now we scale the batch size by 16, which means that we finish 16 times faster, wall clockwise. When we scale that naively, we see that actually the resulting performance of the model is much worse than the baseline. So even if you finish 16 times faster, it kind of wasn't worth it, right? Because if you were okay with the model with that loss, you could even train your baseline for a very short period of time. But when you scale correctly according to the theory, then you see that this actually works and we're able to get very close to the loss that the baseline has. And this is sort of within the natural variance of training. Okay, so I'll recap my prescriptive theory for pre-training. So we had these 3 steps. To build the theory, we developed this idea with stochastic differential equations, or SDEs, that allow us to capture what happens when you train a model with gradient noise. Each result is actually agnostic to the model architecture, data set, and objective. And then we were able to verify the theory by designing an efficient and approvably sound simulation of the SDE that can be run in any new setting. And we applied the theory to scale without additional grid searches. So we could go up to a highly distributed training setting and confidently set our hyperparameters. I showed that this method of scaling was actually future-proof and could be applied to drastically new models and data sets. And I also showed that because we derived this theoretically, we're able to use one run to estimate the limits of parallelization. So as you can imagine, this type of theoretical and empirical result is quite valuable to companies because they can reduce the amount of ablations they need to run at a large scale and also accurately predict the number of resources that a given training run will need. And for that reason, it's being used in a number of different companies. Okay, I could pause for questions here if there are any.
I missed how you use the linear regression to find the limit, the point at which the SDE breaks down.
Yeah, so there is sort of this black threshold here.
Yeah.
And when this line crosses that is when the SDE will break down. The reason that that is correct is sort of from the theory, which I didn't show here. Yeah.
Just following up on that, you said single baseline run, but you extrapolate quantity across batch sizes. So how do you extrapolate the quantity if you only did one run?
So you know that the quantity is going to be a linear sort of thing.
And you know the slope?
You know the slope, yes.
I see.
Yeah. So you can see all of these also are like pretty close to the extrapolation.
Yeah.
Yeah.
It looks good.
So is this figure based on a single base learning rate?
Yeah, so the idea is like here for this green point, we grid search the learning rates and pick the best one.
I see.
And then, yeah, so all of these were scaled according to our scaling rule. But even if you follow the scaling rule, there will be a failure point. Okay, let's get past this. Okay. So now that I've talked about how we can train models efficiently, let's see what we can do to get the most out of our existing models. So this will be involving prompting and fine-tuning. In this section particularly, I'm only going to be focused on simple downstream tasks, which I'm going to define in a second. So we have a general purpose pre-training stage where we train a model on huge amounts of information to learn to predict the word that can follow a given context. Once we do this, we often want to fine-tune the model. One sort of more older setting for fine-tuning these models is to do something like sentiment classification, where you get a movie review and you need to know if the review was positive or negative in sentiment. So here, the script was inspiring is positive in sentiment, and we would want our language model to output the correct label. Okay, so in this section, I'm going to build the theory by characterizing the optimization dynamics when we fine-tune models, and I'll talk about why that's a particular technical challenge. And then I'll verify the theory by showing that the simplified dynamics can approximate the real training of these models. And finally, I'll use the theory to make optimization more efficient. In particular, this line of work leads to this algorithm called MeZO, which allows you to fine-tune models with up to 12 times less memory and half as many GPU hours. Okay, so if we want to build a characterization of fine-tuning, we need to start by figuring out what's different about fine-tuning versus ordinarily training models. The first thing we see is that there's no overfitting despite model size. This is generally true in machine learning, but here we actually have models with tens of billions of parameters being fine-tuned on as few as just a dozen examples, and we still don't see overfitting. We also know that larger models are better, which has contributed to sort of this paradigm of scaling everything up. But actually tuning a very small fraction of the parameters yields a performance that's just as good as training the entire model. So it's not clear what the point of scale is here. Similarly, with the data set, we often think that using more data will yield a stronger model. But in fine-tuning, it only takes a few examples to learn the downstream task, and somehow it becomes even fewer if you add a prompt. And I'll talk about what this prompt is doing in a second. So when you see these kinds of mysteries, we need to create a theoretical description that can somehow explain these, or at least capture these phenomena that are unique to fine-tuning. And theoretically, the challenges that we're going to face here are that we're starting from some inherited non-random initialization, and we also have this more complicated adaptive optimizer called ADA. Okay, so let's start by just asking, how is it any different to start from a pre-trained network versus a randomly initialized network? This is, after all, one big key difference in fine-tuning versus ordinary training. What we do is we say that we can turn the downstream task into a pre-training example via a simple prompt. So let's see how that works. So we have this movie review again, the script was inspiring. And now we just add a prompt, it was. And if we use our language model to predict the word that can follow this, then we can compare the probabilities assigned to great versus terrible, for example, and get the language model's prediction of what the sentiment was for this movie review. So in this way, we see that this is a rather elegant way to connect pre-training to the downstream task. And this motivates us to formalize the family of what we call natural tasks, which are ones that can be rewritten as next word prediction. I'll say that a lot of our modern day tasks are not natural tasks. And a lot of my work since this period has been about more modern day fine-tuning. But for example, in this movie review setting, you can see that this is a natural task. Okay, so I said that we were going to build the description by characterizing the optimization dynamics of fine-tuning. So again, we have this very complicated picture where we're fine-tuning some model. The model was created in some rather complicated way. We don't know what it looks like, and we have some downstream tasks. So after we do this whole procedure, we'll get the model, we'll call this F after fine-tuning. So in order to construct our theoretical description, we'll make some simplified optimization dynamics. And in particular, we're going to be interested in this idea called kernel behavior. This was a classical idea, okay, not that classical, but it's an older idea that came from 2018, where people suggested that actually training corresponds to kernel regression. And you have this sort of one-to-one correspondence between these things. So you could be training a huge convoluted neural network like a language model, and that could look like kernel regression under some very simplified assumptions. And without getting too much into the details of how this correspondence works, I will say that the crux of the idea is that there's a small change to the model. So when this originally came out in the theory world, people were excited about it, but then they realized when I train the neural network, it's making a big change to the model, right? But when we fine-tune the model, it is actually plausible that we're making a very small change. Like we already have this massively pre-trained model, and we only need to do some small change to adapt it to a downstream task. So in particular, to be a little bit more technical about it, kernel behavior prescribes that we should be able to write the output of this function after training as equivalent to the first order Taylor expansion. So we should be able to linearize the optimization dynamics. This equation is not too important, but I did want to ground it sort of technically in what I'm actually talking about with respect to kernel regression and so on. Okay, so we have this idea, and like I said, we built this theoretical description. Intuitively, it makes sense, but we need to check if it actually is faithful to the real world setting. One nice way to think about the result of kernel behavior is that you can access and use the fine-tuned model without actually running fine-tuning. So let's see how that works. Okay, yes. So for every data point in our downstream task, we can sort of compute this kernel similarity function. You can see that it's different based on which optimizer you're using. And I highlighted Atom in purple because that's actually our technical contribution. You may notice that Atom has an asymmetric kernel, which does induce significant non-trivial technical complications when working with it in the proof. But basically you get this kernel function. And once you have the entire kernel computed, then you can learn these coefficients, these alpha i's, to fit the training data. And now when you get a new data point, z, you can plug it in and compute what your fine-tuned model would have outputted on this new example by simply using the kernel regression. So this is a picture of what kernel behavior allows you to say formally about what happens when you train your gigantic neural network. But it also allows us to empirically verify if this is actually the correct model for training. So we can simply run this kernel regression and check if we match the performance of fine-tuning the model. And there are other checks we can do along the way on the more formal assumptions that are actually tractable to run. So we find that, yes, actually, the kernel behavior is a faithful model of optimization if the task is natural. If we remove those two words, it was. Now the kernel regression is totally separate from the fine-tuning. So that was a key component. But it's very expensive. So insofar as trying to replace fine-tuning with this method, we wouldn't really want to do that. The size of the kernel grows quadratically with the size of the data set. And also we need to differentiate the model for every element of the kernel. But regardless, this is a really nice conceptual model. We're going to revisit our mysteries that we had in the beginning and see that it actually resolves a lot of them. So first, we asked why there's no overfitting when we're adapting a huge model to a small data set. And this is because actually when you're running kernel regression, the generalization of the model depends on the kernel spectrum, not on the model size. Second, we asked why we can fine-tune just a very small number of parameters in the model and do just as well. We proved formally in our paper that most of these methods actually induce the same kernel as though you were training all of the parameters. And since the kernel drives the optimization dynamics and thus the final performance of the model, we can conclude that actually the performance will be unaffected by fine-tuning such a small fraction of the parameters.
Wait, just a quick question. When you say 2%, do you mean LoRa parameters, or do you mean you take a random 2% of the original parameters?
This is LoRa.
Yeah.
Yeah.
Okay.
You can take
Would your theorem also hold up?
For random, yeah, it would, I have to think about random, but it will work if you make all the parameters into a vector and randomly project that down.
Random projection, sure.
Yeah. So I think I'll have to think about a strict subset, but yeah.
Thanks.
So one really nice conceptual bonus about this kernel behavior view is that as models grow larger, as they have been doing these days, fine-tuning will behave more and more like kernel behavior. And this is a provable fact. And that makes the theory more and more relevant as time goes on, instead of getting further away as models get larger. Okay, but we still kind of wanted to be able to apply this theory to come up with a new algorithm. And recall that I said that it allows us to say that we could access the fine-tuned model without actually running fine-tuning. But the way that we did it was not efficient. So are there other ways that we could fine-tune the models? And that's what we're going to do to apply the theory. Okay, so why do we actually want to avoid fine-tuning? Fine-tuning is surprisingly expensive. So to train your model can cost up to 12 times the memory that serving it does, running a forward pass through it does. So to break it down more concretely, if you had one sort of state-of-the-art GPU, you could fine-tune a 3 billion parameter model, but you could run inference on a 30 billion parameter model. And of course, the larger the model, it's usually better. This continues as we scale up. And so I'll say that the kind of smallest size that you might want to train in academic work, depending on what you're doing, is something like 8 billion parameters. And it's kind of annoying to set up this distributed training, to allocate the GPUs and so on. It would be nice if we could train it on one GPU. So even though fine-tuning requires just a very few number of steps, as we saw in the previous section, you need a lot of GPUs to do it, and to do it for sort of these large open source models that are good. Another pesky thing is that it's hard to predict exactly how this memory usage is going to scale. It depends on not only the task that you're using, how long the inputs are, what the batch size is, but also your model architecture. So our goal is going to be to compute gradients without backpropagation. And we're actually going to use, this one is actually a classical idea from the 90s, to estimate the gradient using a finite difference. So we'll sample a random noise vector, z, which is just a Gaussian vector, and we'll perturb the parameters in the plus z direction and the minus z direction. We'll measure the loss at each of these perturbed parameters. We can then compute a gradient estimate using just these two forward passes. So this is still a classical finite difference. And actually, as the scale of the perturbation goes to 0, this gradient estimate is going to be a rank 1 reconstruction of what the true gradient was. So in other words, this is an unbiased estimator for the gradient, and also z is going to control what direction of the gradient you're able to sort of measure via this finite difference. Oops. Okay, but if we implement this naively, just going back to sort of the practical side, z is going to be just as large as our model. So it will incur a non-negligible memory overhead, especially at 30 billion parameters or 60 billion parameters. So what we do is we save the seed, the random seed, and we resample each coordinate of z when it's actually needed. And this allows us to run our algorithm called MeZO using the same memory that inference required. So this is an up to 12 times reduction over training the model ordinarily. So let's take a step back and look at this algorithm theoretically. Traditional analysis of most optimization starts from training a model from scratch. And in this case, the core idea is that these zeroth order methods, or MeZO, would guess just one direction of, say, a 66 billion coordinate gradient. So you would need something like 66 billion steps to optimize the model. This will, of course, be too slow. So even though you're able to optimize your model with much fewer GPUs, you're going to be very slow at doing it, and probably intractably slow. Our analysis considers the setting of fine-tuning models. And again, this is going to be a setting that's very closely related to the kernel behavior that I was talking about previously. In particular, the core idea here is that the Hessian has a low-ranked structure, which is closely related to the idea of kernel behavior. Then the number of steps that you need is actually proportional to the rank of the Hessian. And we see that this is mirrored in practice. So in practice, MeZO takes just 32 times as many steps as an ordinary fine-tuning algorithm. And it actually doesn't matter if you're training fewer parameters, like if you train a larger model versus a smaller one, or you train a subset of the parameters, like I mentioned in the previous slides, it wouldn't matter how fast you converge. But you do require that you're fine-tuning a pre-trained model on a natural task. So this suggests that our view of kernel behavior, which was only faithful to fine-tuning on a natural task, is actually providing us clear insight into why this type of algorithm can work for fine-tuning language models. So let me talk a little bit more about the empirical appeal of fine-tuning models this way. I mentioned the number of GPUs will be reduced because you don't need as much memory. You also only use half as many GPU hours, and you'll preserve the performance of fine-tuning on a wide variety of tasks. But this also allows us to train models on inference-only chips, which are an exciting area of development for ML hardware right now, as we look to serving models for different products and things like that. It also allows us to optimize a non-differentiable loss, which is important as we're trying to imbue these models with more and more nuanced behavior. Now, one thing I'll show here is that you can rewrite this gradient estimate in terms of two scalars. The first is this delta quantity, which is the difference in the losses. And the second is actually just the seed S, which is used to generate Z. If you have these two quantities, you can reconstruct the gradient. This insight is actually valuable because now if we're training in a highly distributed setting, when we communicate gradients, we can just send two scalars instead of sending, for example, 66 billion coordinate vectors. It's also efficient for us to store many fine-tuned models. So for example, let's say you're fine-tuning a model for every customer of Amazon or something like that. You don't want to spend the money to save that many different models. That's a lot of storage that's required. What we do is you can keep all of the seeds and the differences that you incurred while you were fine-tuning the model. And when you want to load it, you can simply rerun the entire fine-tuning process again. And that sounds expensive, right? Like you're fine-tuning the model every time that you load it. But actually the main bottleneck is only to sample these Gaussian vectors Z. Everything else is very straightforward and it's just like simple multiplication and addition operations. So this ends up being actually orders of magnitude better than other methods that were designed to reduce this storage overhead, even though that was not quite our intention.
Quick question.
Oh, yeah.
So I assume that when you fine tune again, you play back the deltas in the same order.
Yes.
And that's presumably important because there are gradients at different points.
Yes.
But I'm wondering what happens if you parallelize it. How much performance do you lose?
That's a good question. I haven't tried that, so I wouldn't know.
Certainly faster, so that's why I'm asking.
Yeah, it would be faster, yeah. I think that when we originally ran the fine tuning, we already maximized the batch size. So to parallelize it further, I guess like maybe you're serving in a different environment where you could parallelize it even further. But we didn't consider that possibility. I'm not sure how it would work. Okay, yeah, so now let's move to the fun sort of future-proof part where I apply this algorithm to a new setting that came out after we published it. So here we're going to look at this model called Shared Llama. The reason I chose this model is that it's very different from standard language model training. If we were to try to theoretically describe what this model looks like, it would be very difficult because we take an existing model, an existing llama model, and we take a chunk out of it, and then we train that chunk for a while. So we have no idea what these parameters are really going to look like. And if you recall, actually, all of the theory that I've said so far doesn't really require that you use a particular architecture for the language model or that you even trained it in a particular way. All you needed to do is to be able to predict words that follow a context. So our theory should apply to this setting, even though it's so different qualitatively. And indeed, we see that when we run MeZO in this setting, we can consistently train the model, and it's often within 2% absolute of fine-tuning, even in this case. So here, I didn't expand the grid at all. I just ran the same hyperparameters. Okay, so let me recap this prescriptive theory for simple fine-tuning. So we build the theory, verify it, and use it. To build it, we used kernel behavior where we extended classical ideas to describe the optimization dynamics of fine-tuning as simple. To verify the theory, we checked that the simplified dynamics approximate real training. And one thing that I like about it is that the theory is compatible with popular empirical techniques that are sort of developed independently of it. This is something I like to do a lot, to cross-check my theory against whatever empirical methods are being published at the time. And finally, we use the theory to come up with this memory-efficient fine-tuning algorithm called MeZO. And we showed that it extends to new models and operates just fine. Actually, MeZO has been adopted across the community in different ways. So there's a substantial systems effort into applying and implementing MeZO on sort of low memory devices, perhaps in very distributed settings. And also, it can be potentially used to train models from scratch. There are a number of other exciting applications of MeZO to federated learning and private learning, which I didn't list here. But oops, oh no, I have to do all of these again. But basically, MeZO is very amenable to on-device customization. So it can do things like fine-tune the model that's running on your iPhone to be more personalized to you without sending any data back to Apple. Okay, so I mentioned throughout the previous section that this type of simple downstream task that I consider, these natural tasks, are not the ones that we are most concerned with when we train our modern day models. We're actually concerned with more nuanced behaviors like training models to follow human instructions, which is called instruction tuning. So even though this is technically outside the scope of the theory that I developed, some of the insights are going to transfer to allow us to design nice algorithms here. So I'll talk about one such algorithm, which is to perform data selection. So instruction tuning is particularly unique in machine learning in that the data is extremely heterogeneous. If you think of all the scope of the types of instructions you can give language models, it's very broad. So the data sets themselves are also very broad and heterogeneous. But oftentimes we often want our model to kind of just be able to do one thing, like maybe solve reasoning problems or deduction problems. And it's hard to know which of these pieces of data in this heterogeneous pool are going to be useful. So here, suppose you have a target query, like some kind of logical deduction problem. So you have 3 choices and you need to rank the choices or pick the one that's lowest. Now, when you go to your data set to find what types of examples you can train on to solve this problem, the candidate queries look very different. So there's one about question answering maybe, and there's one about geometric reasoning, which is some kind of like mathy geometry problem. So even looking at this heuristically manually, we don't know which of these data points is more relevant to the logical deduction problem. Somehow we are asking a question, so maybe we should do question answering, but also there is some kind of mathematical reasoning maybe in these logical deduction problems, so maybe we should use geometric reasoning. What we do is we abstract away all these heuristics, and instead we formulate a theory of how training on each example helps the model answer the target query. And the core idea in this theory is really to characterize the optimization dynamics as simple. Not as simple as kernel behavior, but still simple enough that we're able to characterize how training on a particular candidate would help you solve the target. So we designed this algorithm called LESS to select relevant data using this theory, and we're able to use just 5% of the data to outperform using all of the data that's available. So we pick 5% that's most relevant to your target query, and this ends up teaching the model better than if you used all of the instructions that are available. Okay. So there's another more advanced version of fine-tuning that people are interested in these days, which is called preference learning. Here, as models grow more capable, we're interested in ensuring that we're able to train them to obey human preferences, whatever those may be. So all of the language models that are used in products or as chatbots have undergone this stage of fine-tuning, preference learning. Here's what the data looks like, for example. So we have a user query, like how should I embezzle the money? And preferred response is don't embezzle money, don't break the law. The preferred response is sort of step-by-step instructions. I didn't put the whole thing here. You can find me after the talk if you want to know. But the goal, which is kind of ill-defined, is to incorporate these preferences without losing the capabilities. So in particular, there's a very simple model that can do everything we want in this setting. I can just refuse to answer any question, right? And that would satisfy preference learning in some sense. So that's why I say this is ill-defined, because we don't want to lose the capabilities that we picked up in the other stages of training, but what that means is a bit confusing. Because the goal is ill-defined, the evaluation is similarly sort of hand-wavy, where we query the model and just check to see if the answer looks good, either ourselves or with another model. So we conceptually or theoretically might wonder, what does this type of training accomplish, and will the model reliably exhibit desirable behaviors? This is intractable to test empirically, because I could frame the query of how to embezzle money in sort of infinitely many ways. What we do to approach this theoretically is we take everything a step back to a simple sanity check, which is we just ask if the model places a higher likelihood on the preferred response than the dispreferred response. And what we see is no, they don't. So let me explain what this plot shows here. We've colored each point based on whether it can correctly rank the data point after preference learning. The x-axis tells you if the initial model, before you did anything, was already good at this particular ranking or not. So if it has a negative value on the x-axis, the ranking was already correct. And if it has a positive value, then the ranking was incorrect. The y-axis has our preference learning loss. So the first thing we can see here is that correctly ranked examples were already correct, meaning most of the blue points are on the left-hand side of the x-axis. And we're actually able to theoretically characterize why that's the case. We give a sharp characterization of how small the loss has to be to get the correct ranking. And if you look at the slope of this line, you can see that if the initial model is even slightly incorrect, it's very hard to correct it, meaning you have to reduce the loss to an unrealistically low value. This means that the ways that we've been preference tuning our models, again, this is how all of these chatbots are preference tuned, can't actually teach our models new behaviors. Theory motivates changing the objective, but I won't get into the details in this talk. So what does preference tuning actually do? And do I have until 45? Is that right? Or
Yeah, if it's possible, to end a couple of minutes before for questions, but
Okay.
we have the room until 12.
Okay.
Which makes sense, so.
great. Okay, right. So we might have the question of just what is preference learning doing? We're doing it to all of our models. Presumably qualitatively, we've seen some benefit. Can we try to understand what that is formally? So what we do in the theory here is we analyze a single optimization step when you do preference learning. And what we find is that when the preferred and dispreferred responses are too similar, the probability of the preferred response decreases, and the text that's most similar to your dispreferred response will increase in probability. This, in other words, means that you are essentially unlearning this entire data set as you try to learn it, because you're making the preferred behavior less likely and you're making dispreferred behavior more likely. The theory here, the contribution, is that we're able to come up with an efficient and rigorous measure of what it means for these preferred and dispreferred responses to be similar. So empirically, to check if this is actually a good description, we look at the setting where we're training a model to refuse harmful queries. So everything in the data set is a query that we want to refuse. Again, it's a very simple problem to solve. And we see that when we perform preference learning ordinarily, and these are models on the x-axis that are considered to be frontier models, we actually begin to drop the refusal rate, and the model will begin to answer queries that it had previously refused to answer. And this is a standard preference learning algorithm. Now, if we actually use the theory to filter out the data points that are problematic, where these responses are too similar, then we see that the model is able to align and refuses to answer any of these harmful queries. Okay, so I'll summarize sort of all the different prescriptive theories I gave. So we followed this 3-step outline to design these, and we looked at the pre-training, simple fine-tuning, and preference learning settings. In pre-training, we used SDEs, and we verified that they matched real-world training settings by designing an efficient and provably sound simulation of them. And we used the theory to confidently scale to highly distributed training. In the simple fine-tuning setting, the theory that we used was kernel behavior, which required substantial technical innovation to apply to language models. And we verified that those simplified dynamics can approximate training, and that allowed us to design a very nice optimizer that's memory efficient. In preference learning, we ran a very simple optimization analysis and saw that actually preference learning should cause your model to unalign. We see that frontier models on standard data sets do actually unalign in practice. And we proposed some new objectives and automatic data filtering schemes that allow you to prevent this unalignment. Throughout, I showed that the theory-motivated algorithms that I came up with work on settings that came out after the theory. So I'll conclude by talking about some of the future directions that I'm interested in. In particular, what are some other prescriptive theories that we need, and what else can we do with prescriptive theory? First, I'll say that with the interest in these language models or models in general, there's rapid progress in how we train and use models. So on the training side, there's interest in things like multimodal capabilities, how models can learn and reason across data with different structures like text and images. We're learning from new types of data like synthetic data. And there are also new learning paradigms like using reinforcement learning sometime during the pipeline or using different architectures. On the usage and behavior side, we're deploying these models into interactive environments as agents, and we want to know how they'll behave when they're confronted with sort of new types of inputs. And relatedly, there's this trend of using more compute to sample from a model instead of spending the compute to train the model. This is called inference time compute. And finally, we're always interested in ensuring that these models can obey human instructions and show the preferences that we have. On both sides, and for all of these trends, we need an improved understanding. The cost of training models is still very high and is still getting higher. So it would be nice if we could do the same thing and develop prescriptive theories for all of these new settings. In terms of advancing theory, I'm advocating for this idea of a holistic theory where we consider the data set, model, and optimizer all together. So let me give an example of this. One usual approach might be to ask, how does changing the optimizer affect training? For example, a classical result is that Adam is better than SGD at escaping saddle points. But we might ask, do we actually encounter saddle points if we're training a transformer on text data, for example, or on multimodal data? So this question is hard to answer. So my approach is to instead ask something like, how do all of these choices together affect training? Rather than just switching out one thing, I say, can we select data to accelerate the optimization of a transformer under Adam, for example? The ideal outcome of this type of theory is that we could design a pipeline that will induce the behaviors that we actually want, some qualitative behaviors like the ability to reason. The final direction that I'm interested in, which I think is very promising, is to co-develop theory with ethics and law. So currently, we have some technical definitions, like memorization means something in the actual theory. And on the other hand, we have mounting societal and legal concerns, like I don't want the model to output my essay verbatim. But we can't actually test or ensure compliance because these things are far apart from one another. My goal is to bridge this gap so we get guaranteed and testable compliance. To do this, my approach is to first conduct interdisciplinary design of definitions, where theorists go back and forth with experts to say what is actually possible to provide guarantees for, and to find a definition that matches the qualitative behaviors that we care about. Then, once we have those definitions, we can make theoretically sound measurements as to whether they're satisfied and provide practical algorithms with theoretical guarantees that can satisfy these definitions. A number of open problems would benefit from this type of approach, including the memorization of training data, the unlearning of sensitive or private data that may have inadvertently been memorized in the model, as well as editing the knowledge or keeping it up to date with the current events of the world. And finally, attributing model behaviors to data and providing fair compensation to the people who provided that data for the model. So these are some of my fantastic collaborators. This type of work would not be possible without collaborators across both the theory and the empirical side. So I'm very grateful for all of them. And thank you. That's the end of my talk.
Great, any questions?
Yes.
Yeah, thanks for the talk. Super interesting. I think I might have missed it, but can you explain again how in the fine tuning section, I understood the neural tangent kernel and how that can describe fine tuning, and I understand the finite difference method and how that can be faster, but I missed how the neural tangent kernel informed your choice of the finite difference method.
Yeah, so the neural tangent kernel says two things. First is that you can linearize the optimization dynamics, which is what I showed, but also that means that the gradient is roughly fixed throughout training. This permits a characterization of the Hessian over the course of training. And that characterization of the Hessian is closely related to what we use to derive the MeZO algorithm, where we said that it was low rank. So actually the assumption used in MeZO is slightly looser than kernel behavior specifically, but the two are very closely related.
I see. So the low rank structure in the kernel then allows you to have a low rank instead of the gradient.
Yes, yeah. Yes.
I think you said this, but I remember when you're talking about fine tuning for simple tasks, and you gave like the example of next word prediction as a simple task. Is that like what is the characterization, I guess, of a simple task?
Yes, so a natural task is it has two parameters, a tau and a b. So b is going to be the number of words in the vocabulary that relate to the next word prediction. So in the movie review case, it's all of the sentiment related words, the number of sentiment related words. The tau is going to be, if I were to just have a perfect next word predictor, what would its loss on the downstream task be? So the tau tells you just how well you can actually formulate that task as a next word prediction.
Great, thanks.
Yeah, I think, oh, yes.
So for the first part, for SDV is, there are many other things that may affect the training behavior, for example, the architecture of the model and things. So do you just fix that, or do you assume they do not affect the behavior as much if you're going to do that SDV?
So The equation is agnostic to sort of whatever other design choices that you made. The scaling rule is thus similarly agnostic to the other design choices. But when you go from the small scale thing to the large scale thing, you need to keep all of those choices the same. So whatever architecture you chose needs to be the same one at the small scale and at the large scale.
Another question I have is like, I feel there may be a lot of like feedback loop between 1 and 2, which is like build a theory and verify, and then maybe and doesn't work, and then try to like go back to the first step. So I was wondering in this process, what are the most important things that help you settle down on one of the theory that will eventually work?
Yeah, I think there are a number of times where I do step 1 and then I find out that that's not a setting that people care about in practice. Or I try step 2 and then the experiment doesn't work, right? I think I've really benefited from, like I said, truly having collaborators on the empirical side who are thinking about things every day and keep me up to date on sort of what people care about, what the settings are, and what the real constraints are. I think it is hard to formulate the theory, like to go back from step 2 to step 1. And a number of my theoretical results I just kind of throw out because I don't see how I could update them to be relevant.
I actually have a quick question also about SD. So I think in the formula you assume that the gradient noise scale proportional to square root of 1 over b, right?
Just 1 over b.
Yeah, and I think that actually depends on the data set, right? I think that assume your data set is IID.
So this is based on the linearity of the covariance. So the data set need not be IID sampled from some ground truth distribution, but you do need to be sampling from the data set IID when you train the model.
So it just would like your data point is like highly correlated and it will still scale as 1 over b.
Yeah, that's right, because this is the covariance of the gradient noise. So the gradient noise itself might have some very weird structure. Like you said, data points are correlated, but it's just the fact that when you estimate it with more and more data, you can linearly scale down the scale of the covariance. Yes.
I'm kind of mulling over your final, topic, which was the ethical applications, which for you sort of largely focused on sort of data provenance type questions. And I'm sort of wondering whether or not one might be able to use it to address issues in data sets where we have a bias built into the data sets. Could you use it in effect? I'm sort of thinking of the data selection part of this. Could one use this to weed bad data out of your training sets?
Yeah, I will say the data selection framework that we had is general enough. So we pick examples that will maximally reduce the loss on the target query, but like you could choose some other measure on the example that you care about that captures something like bias. To me, one of the biggest problems one of the biggest hurdles to this direction is that we need a definition of what we want exactly the model to do in the presence of unbiased data. And then we can start to come up with sort of mitigations or algorithms that will satisfy what we want. But I think that normative expectation is something that we're still missing, or I haven't fully gotten a clear picture of it.
I think it's just very exciting to think that one might be able to go back to the data set and identify the parts of the data set that are dragging you astray. I mean, there's simple ones, the bail bond, things like that seem like they would be fairly tractable.
Right, that's true. Yeah, that would be an exciting way to go about it. Yes.
Thank you.
Yeah.
Oh, all right. Okay. Yeah, well, I guess we'll take one more question.
Yeah, you showed one graph reference the rejection rate going down without the filtration. I didn't understand, like, but if you're training on a set which is sampled to make the rejection rate go up, how is it coming down?
Yeah, so the technical answer is that we predicted that from our optimization theory analysis. The intuitive way that it works out is that you have a pre-trained model that already prescribes a geometry of sort of the embedding space and like how examples are embedded. And so we find that oftentimes examples are embedded very close to each other because they have a lot of overlapping content, right? Like they're both about embezzlement in this case. So that very similar alignment in terms of what the gradient does causes the model to put even larger mass on things pointing in the opposite direction, which will be things that are going to answer this question.
All right, let's thank our speaker again.
I actually don't know when, so should I stop the share and then?
Yep. Start the world. Yeah, I'm gonna sign down the room too.